Okay, hello everybody, Happy New Year. Do you remember last class? What we spoke of the last class, in the last part of last class?
Linear models.
Yeah, we were speaking about linear models in general. That was probably the first part of the class when we did the height versus weight, kind of connecting two variables. But then we say that not always the relationship is a line, I mean a straight line. So not all lines are straight. And we gave an example, for example, when cells grow, they grow exponentially. And exponential growth is an important case. And there are other cases that they grow, how can I say, with a power law. We will give you a little more detail today, but it was like the number of cells. If you measure the size, in the colony in Petri dish will grow like a circle, and the area is essentially depending on the number of cells. But at the same time, the area depends on the radius. So if you measure the radius, the number of cells is not a straight line, kind of a square root relationship. Square root is not exponential, but it's not a straight line. So we have these three cases. And I give you a specific example that was intended to scare you, that it was called robots are coming. You remember? That robots are coming to take your job? Huh?
Yes.
Yeah. So, and that was the exponential growth of the computing power and of the data. I mean, data can be created every time faster. In particular, molecular biology data is every time cheaper and faster. And analysis of data is every time cheaper and faster. So it means that robots will do many of our jobs. So we better do something that the robots cannot do. Okay, we will continue this idea. So so last time we showed graphically that applying logarithm was a good idea to see more details. There was an idea that if the numbers are small, the law kind of make the smallest bigger and make the biggest smaller, so they are easy to compare. So I will start with the mathematical part of this, and you will be happy to know that there is not a lot of mathematics. And my theory is that the only need, no, not the only, but the most important thing that people need to know in biology is logarithm. Logarithm is really something that you cannot avoid in biology. And you find it everywhere. Wherever you look, you will find logarithm. You don't need trigonometry, for example. Most of molecular biology, you can live without any cosine or any square root of something. No. But logarithm, sooner or later, you will find it everywhere. So there is a basic thing. I mean, the point is that I cannot give you the full concept here because you need to practice. I will give you just the general concept, but in real life, you need to practice it. So if we have the chance, I will give you exercises that you can calculate some logarithm, essentially to gain facilities. Like, well, it's like every tool. You need to practice it to really know it, to make it automatic. So you don't need to think about it. You just do it. And when you do that, you have a new tool for thinking that will allow you to do things that you cannot do easily without this tool. There are many, many things that logarithm is really an important tool of thinking. In fact, in my class of methodology of scientific research, I have essentially one chapter about logarithm. It's really super, super, super important. Okay, so logarithm is a kind of inverse of power. If the p to the power of m, you want to undo this, there are two ways to undo it. One is the root, and the other is the logarithm. So if x happens to be p to the power of m, then the logarithm of x in the base p is m. That is kind of definition. Practical example, 10,000. If you want to know what power of 10 is 10,000, in other words, if here P is 10, to which power I have to raise 10 to get 10,000? I think everybody knows. You count the zeros here. You have 4 zeros, no? Agree? Okay, easy, no?
Yep.
Yeah, that is the idea. That it's kind of counting the size of, I mean, essentially the number of digits. That is one of the reasons why this is important. The number of digits correspond to the logarithm of the number. It's proportional to the logarithm of the number. And let me just give you a point that essentially means that the information contained in a number depends on the logarithm of the number. And I will give you something more. The other name of information is entropy. So when you get this thing, you really get to thermodynamics and things that are very crazy, but very, very powerful. One of the important ideas that people invent. Anyway, so, but the basic concept is this, that you count the number of zeros, or the size of the number, and you get a smaller number, okay? Now, why 10? 10 is useful for us because we have 10 fingers, and it's easy for us to think. For computers, and in truth for biology, it is also used to think on the base 2, because when cells duplicate, you get you multiply by 2. Every cell duplication you multiply by 2. So the number of times you multiply by 2, which is technically called the fold change, is multiplying by 2. So in many cases when you measure gene expression, you take the logarithm of the gene expression in base 2. But so, for example, if you wanted to change to base 2, it's not very hard. And in fact, my basic point is that the base that we choose is kind of irrelevant. The important thing of logarithm, the properties of logarithm, are very much independent of the base that you choose. If instead of P, you want to use Q, you get a little math, you get this thing, you get essentially the same M that you had before, multiplied by a constant, the logarithm of P2. So to move from P to Q, you multiply by a fixed number. You calculate that fixed number only once, and you will use it million times. So they are essentially the same. The curves, if you draw the graphic, is the same. Just there are factor of scale. It's like, let's say, one is measured in centimeters, the other is measured in inches. Okay, distance are the same. Only the tool that you use for measuring is different. Okay, that is the nature of logarithm. Different bases essentially mean different units, nothing else. The logic is the same. For example, if you want the same logarithm that we have before, but in base 2, it will be 4, which is the logarithm of 10,000 in base 10, times this factor of correction, logarithm of 2 in base 10, that is 3.3, and you get, you do the multiplication. You can, if you want to convince yourself, you can calculate this and this. In R, we have the function log 10, and log 2. So which is the best one? Well, the best base, well, at some level, it doesn't matter. And the one that we choose is really for practical reasons, and we should be free to change them. But for our case, the one that happens to be more practical, because it's kind of easy to write, essentially, is the natural logarithm. So if the natural logarithm is essentially the inverse of the exponent function. And that is probably the trick, that there is a function called exp that give you a number, and the inverse of that x is log. That is what we need here. If you have a log that is the natural log, then x will be the inverse of that one. And that is why in most computer systems, well, there is another reason that it is, for a computer, it's much easier to calculate natural logarithm than others. Internally, computers only work with natural logarithm, And then they multiply by factors to get in different bases. So in R, log is natural logarithm. You can realize this if you take logarithm of 10,000. It's not 10. It's not 4 like we had with the base 10. It's not 13 like we had with base 2. It's something in between. That essentially, well, you have to be more careful if you want to prove it. But essentially, what we can see here is that when we use log in R, it is not log base 2 because the number is different, and it's not log base 10 because the number are different. Okay, so to solve the mystery, what I'm saying that the log that we have in R is the natural log. What happened here is the natural log. In other words, with the base e. Okay, everybody knows that, no? We can talk about e forever. It's super interesting, and maybe one day we should do that. We really need a class of mathematics for biologists. Okay, a couple of things that we need to keep in mind. Well, first, this only works for positive numbers, not with 0. That eventually can be a problem because in some cases we have data where the value is 0 and we cannot work. So that is kind of a limit of the tool. Sometimes you want to use it, but you have many values that are 0 and then you get in trouble. So it doesn't work with 0. It's a limit. The second point is this identity. If x is exponent of m, then the logarithm of x is m. Okay, that is the thing that you have to keep in mind. In fact, this slide and the next slide are the only thing that you have to keep in mind, and you can take your notebook, your post-it, and you write this thing. You have to know them for forever. You know, I mean, good students are always writing in the class. You know, maybe I want to make a little parenthesis here because I've been preparing classes all the weekend. And I found a lot of material about how to take a good notes in class. And the point that you have to keep in mind is that your notes should say something that I don't say in the class. I mean, especially because you have my recording, everything that we say will be in YouTube. You really want to write something with your own words. You know, what you really should do in your notebook is to think what you think is important from the class. And you have 2 times for doing this, and they are different. One is during the class, when I'm speaking, there is something that calls your attention, you can take a note. But there is another, like, I don't know, 10 minutes after the class or in the afternoon or after the class that you look back and you say, okay, what was important here? Because after you see all the picture, all the story, you can see the big picture. So it is good that you make a kind of summary every day. It can be 1 paragraph. It doesn't need to be very long, but it's something that you really have to do with your own hands. And I tell you from my own bad experience, because I do this, I don't do this, and then I forget. I look back and I don't remember what was important or not. Okay, so you really have to do it in the same day. Second thing that is important that you have to keep in mind is this, and it is the power of logarithm. Probably the real reason why we use them. First, if you have a multiplication, then the logarithm will give you sum. That is the first thing, that logarithm make multiplication that are complicated into sums that are easy. The second is that if you have a power, a to the power of m, then the m is getting to multiplication, okay? Again, the exponentiation get to multiplication, the multiplication get to sum, okay? It kind of simplifying the problem 1 level, okay? Okay, at least moving, good. You probably know this thing, but I wanted to remind you, and I want you to keep this you write the post-it and you put it here in the computer, okay? Because it's something that this is the point that should be natural for you. Ah, very good. Saying everything, good. We will use it in the following context. We essentially described three kinds of things that can happen. We had the basic linear model in which you have a line with a constant times a slope. Okay, but no, a constant plus the independent variable times the slope. For example, we have the height and the weight of a person depending on the height of the person. Okay, you remember we had that point. Then we have the exponential growth, which is an initial value, and then a growth rate like in the cell. You start with one cell, and then you have a grow. Let's say you grow 20% every day. So this R is 20% extra, 120% in other words. So you multiply by 1.2 every day, and the second day 1.2, 1.2, 1.2, and eventually this will be growing, like we saw last class with the cell growth. So this is the second thing that, and you can imagine this is essentially what the biology happened. At least when there is a lot of food, when there is not too many limits, you will grow like this. Finally, you have you have more things, but for today we have this power law that you have a constant and then an exponent, like how the things are going to grow. So these are the two. You notice there is something here that in all these cases, we have y, we have x, and we have two coefficients. One is the intercept and the slope. One is the initial value and the growth rate. One is the constant and one is the exponent. But there are two variables, two unknowns in every model. Okay. At least at this level. We can have more, but in this model we have two. Okay. Now, then logarithm. We use the logarithm here. Well, the linear model doesn't need anything, it's already linear. In the exponential, you take logarithm of everything, so you have log of y is log of I, this multiplication becomes a sum, and this exponentiation essentially becomes a multiplication, and you have the logarithm of y is the logarithm of I plus the logarithm of r times x. And this is a linear model. Okay, do you see it? So this is the same x. The b, the coefficient b will be the logarithm of the growth rate. A will be the logarithm of the initial value. We only need to do the model not with y, but with the logarithm of y. We have logarithm of y depending linearly on x. The third case, when you have a power law, you have the logarithm of y. You will see what logarithm of y. This c becomes log of c, the multiplication becomes sum, the exponential get out. But this time we have log of y depending on log of x. So note here we have y and x. Here we have log y and x, and here we have log y and log x. Okay, this is what we call a linear model. This is a semi-log, and this is log-log. Okay.
Okay.
Okay, which one to use? My technique, maybe there are better techniques. I play with putting log. I do kind of experiments. It's easy to do with the computer. So for example, I have this, I will give you, I don't know if I have the link at hand, but let me see if we can see. Kleber law, this should be centered. It's a paper. I showed you the number last time, but let's see it again. So I will give you the table. Okay, I will give you I wrote it in a table that we can see here, but let's see the ideas first. And Right now, we see the slides, we'll do practical later. We have the different animals. This table is longer. I make a summary for the class, okay? And they have the weight and the metabolic rate in kilocalories, okay? So these are the basic ideas. So you have small numbers with small numbers and big number with big numbers. So the people think, okay, then maybe there is a relationship between the size of the animal and the metabolic rate. I mean, you need more energy to use a bigger body to keep the bigger body circulating. So the first thing is you put the data, and this is the plot that I showed you last class. Kilos in the horizontal, kilocalories, kilograms and kilocalories in the axis. And you get something that it seems like a line, but it is very hard to say because most of the numbers are cumulating. I mean, what is the name? And there's an accumulation here in the small values. So we really don't see. There are a few big numbers that are probably elephant and whales and something like that that are pulling everything away. So it's hard to see. So last class we say, okay, let's use a logarithm to see what is happening here. But the basic idea is to see if we can also get a straight line. So the first idea was to use log in the vertical. Try to see if this is grow exponential. Yeah, we get more detail, but it is not a straight line. We get more detail. We get more information here. We understand better what is happening because we get some zoom here, but it is hard to make a model. Not impossible, but it's harder. Then we put log in both cases. Okay, this looks much more better, much better. And this is in fact what Kleiber did in 1947. He found that exactly this thing, and you apply log in both cases, and you see something that looks very much like a straight line. So what we do, if we know two things, one, that using logarithm we can bend the data to make it look like a line, and second, if it look like a line, we can find what is the best line. Okay. By the way, in the last class we did last year, we did weight and height, and there was a lot of variability. There was a tendency, but the tendency was not super clear. There was a lot of variability. Here, I hope you agree with me, tendency is much more clear. They are really going in something that is very, very much, the deviation from the straight line are very, very minimal. Don't you agree? Very little. So this really seems like a biological law, and in fact it's something, I mean, it's an empirical law in the sense that we observe it, but there's not a very clear explanation why this happened. Well, the point is this. My proposal and the kind of exercise we are going to do is like I will give you some data and you apply different plots with different logs to see what looks better. Well, there may be other approaches depending on the theory. It depends very much on what kind of theory you have. If you don't have theory, this is kind of an exploratory approach that we don't know anything and we try many combinations and see what happens and see if something fits, okay? And we try to find the theory later, okay? There's a kind of, okay, philosophically, there's kind of the French school and the English school or something like that, the induction and deduction. But essentially what I mean is this: if you have a theory, use your theory. And you will always get something more powerful if you have a good theory. If you don't have theory, you need to explore and try to find some theory, okay? So in this case, we found that the line that looked better was the last one, log, okay? So you remember we just take this formula, this command, exactly like it is, and we put it again, and instead of plot, we say LM, linear model, okay? We store the result in a variable. It can have any name, but I usually call it model because it's the model. And we can ask some questions about the model. We will ask the coefficient of the model. And we get these two numbers, the coefficients. So this is A and this is B, you know, okay? So what is the meaning of this number? Okay, before I want to say something again that we say last class. We do the model sometimes because we want to make a prediction, but in many cases we do the model because we want to know this coefficient. These numbers have meaning, and in many cases we, like I showed you the last class, the speed of sound. The real point was to find the speed of sound. What was the coefficient? Sorry.
Bless you.
Thank you.
Bless you.
Then log. So this finding this coefficient has a value per se. Is not, they are not an intermediate result. They are usually the result of the model. Okay. So I'm replacing these numbers in the formula. What we have is this. The formula was log kilocalories equal to 4.21 plus 0.563 times logarithm of kilogram. Okay? Do you agree?
Yes.
Okay. I mean, I have like half of the people moving the head and the other people are not saying. I really think that if you don't show your camera, you should speak. Okay. So therefore, I'm doing the logarithm using exponential, let's say. So this log goes away. You have kilocalories. This number becomes exponent of 4.21. The multiplication becomes, sorry, the sum becomes multiplication. The multiplication becomes exponentiation, and the log disappears. So I want you to tell me if you agree that this equation is telling you exactly the same as this equation. If this is the first equation is true, the second is true, and vice versa. They are saying the same in different language. Agree?
Yes, I agree.
Good. Then we calculate the exponent and we get this. This is the result. It's a model that is an exponential model. No, no, this is not exponential. This is a power law. So we have 67.1 kilocalories per kilogram times. You have to be careful with the unit. No, this is measuring kilocalories. This is measuring kilograms. So this value here has to change the units. How many calories per kilogram? And this is the exponent. That is the interesting. So, well, one example, one way to think is this: if kilogram is 1, then the exponent doesn't matter. 1 to any exponent is 1. So you will have for 1 kilogram, the consumption will be 67.1. That is kind of this is the constant. Okay. Kind of kilocalories per kilo. Okay. But then this is the result that is called the Claver law. The energy consumption rate increase not linearly with 1 kilo. If you get 1 kilo, you don't have, I mean, if you get 1 kilo, you don't get 67.1 kilocalories. You get less. The increase on metabolism is not linear. You go like 75%. In other words, if the size of the animal increases twice, it doesn't take twice energy. It takes only 75% more energy. Okay? If the size increases 100%, the metabolism increases 75%. Okay? And that is not was not obvious. I mean, essentially, it means that bigger animals are kind of more efficient. They require less calories per kilo. And that is the law that is in the paper. You can Google it. When I say Google it, really clever law. You Google it and say the metabolic rate of an animal scaled to the fourth power of the animal mass. 3/4. 3/4 is 75%. This 3/4 is this one. Okay, but there is a error in the last, but it's part of the error. It's in the margin of error. Okay. Fine. Any question?
No.
That is what Clever did. That is what Clever did. So that is the first point. That what we did is this. We last class we saw that when we have a point that seems to be in a line, we can use this LM to get the best line, and we get the coefficient, and the coefficients are useful per se. Now we say that the same idea can be applied in many other cases using logarithm in a smart way. That you test different things and you find when you find a good logarithm and you get how to draw the line. And the line essentially will not be a straight line, but you get this coefficient and they have a meaning. Okay, but there is also the point that you can use them to predict. So let's make a little prediction. So the models in general are an explanation of the patterns. That is the pattern here is the numbers, okay, that you measure. And the explanation here is, well, at least we are saying that okay, this is a half explanation if you like, but what we are saying is that the number of what we are saying, that the kilocalories of an animal increase with 75% of the mass of the animal, the number of kilos of the animal, kilograms. That is an explanation of how things grow. But the second point is a method to predict what will happen in a different experiment. And in this case, we did this last class also, but I'm just reminding you, we have a command called predict. You have model and new data. Now, there is a little trick that I want to comment you here that new data, we say is a data frame, but if we don't write anything, if you just say predict model, and this is a kind of convenient thing, we get predict with the new data equal to the old data. It's kind of trying to see how good were you to predict the original data. You got me? So let's do that. I'm going to take the predict model to take the old data and see if the prediction is similar to the I mean, if the prediction is close to the old data. Okay? Okay, we have model and we have the original data. So what I'm going to do is this. Clever is the data frame. I'm going to give you the file. And then we have, we add a new column called predictor with mutate. And we assign again to Clever. So this is the pipe. We take the data, we mutate, and we assign to the same place. Fine. It's the way that Zainab likes. She complained when I did to the other way. But what I mean is this is the kind of modern way to do in R. There is an old way that you do column by column. They are both valid. Well, you should be happy with both. I don't know, it's like different tools that you would use in different time. One is a hammer, one is a screwdriver, you use the one that you need, okay? But what we got here, we got numbers. This is the predicted number, and this, okay, kilos is the input, and kilocalories is what we want to predict. The real is 3.6, we got 1.2. 28, we got 3.2. 4,200, and we get 8. So the prediction doesn't look very good, no? What is wrong here? I see the thinking faces. Good. Any suggestion? Any crazy? You brainstorm. You are allowed to say crazy things. You are encouraged to say crazy things. What do you think is happening here? No? Maybe the professor is lying. Maybe we did something wrong. I don't know. Okay, let me give you my version of this thing. What is happening is this. We want to predict the metabolic rate depending on the weight. That was the model. The independent variable is kilogram. The dependent variable is kilocalories. But the model is not made with kilocalories. The model is with log of kilocalories. Log of kilogram and log of kilocalories. So we have to undo the logarithm. Let me show you again the model. I'm going back. So Claver law is okay. This is the model. This is here. Logarithm of kilocalories depending on logarithm of kilo. So since this is the model that we fit here, no? This is the model. The model here is logarithm of kilocalories versus logarithm of kilo. Okay. Now data include the kilo, but the system is smart enough to take the logarithm to make the prediction. Okay. Since we have the formula is stored as part of the model, then we can calculate log of kilo and make make the prediction. But then, when you want to get the result, what the result that you get is the logarithm of kilocalories. To get to the real result, what we need to do?
Exponential.
Exactly. We have to undo the logarithm. So this is a part that we were suffering. So we want to predict, but we have only logarithm. So we have to undo the logarithm doing exponent. Okay. Okay, here is correct. Okay. So predicted is exponent of the prediction. Okay. Now compare the number 3.6 prediction 3.61, 28, 25, 35, 34, 167, 153, 152, 153, 200, 198, 288, 279, 800, 1000, 1000, 1000, 1.2, 1.2, 1.3, 1.2, 1.3, 1.4, 4,000, 5,000, 7,000, and 700, 7,100. It's not perfect because it's a model, it's a simplification. Essentially because you have variabilities. It's clear that different animals, I mean, you have people of different weight that can have different shape, let's say. You can have people that are very tall or people that are very fat and they have the same weight. So there will be some variability, but most of the variability is explained by the model. Okay, not 100%, but a lot of what we see here is explained by the model. Just remember that models are simplification. Let me say it this way. Models are maps, okay? So when you get a map of a city, you will have different map with different resolutions, and you will use one or other depending on what you want to do. If you want a map that is perfect, 100% perfect, the map has to be the size of the city. And that will be probably not very useful. Meaning that you put a map over Istanbul, the map will be perfect, will match Istanbul millimeter by millimeter, but you will have all the city covered with a map, will be very useless. Fine? So yes. The bottom line is that you have to take the logarithm back. Use the exponent in the result. Okay? Visually, it looks like this. Well, I'm not going to give a lot of effort about this part because we are going to discuss doing this plot later, okay? And without the logarithm, the line is a little more, it's not a straight line, but it matches well. Let me see here. In the logarithm, the numbers are very close. There is still an error, and when you do the exponent, that error is increased, no? But this is the basic idea. Fine? And this is the paper. This is the value from the paper. You see that he put the body weight, and the scale is logarithm, but the drawing is the values, not the logarithm, but the straight value. For example, here you have 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 10, 100. So you see that the numbers are not growing linearly, they are growing, they are not adding, they are multiplying. You multiply by 10 every step. Same here, 1, 10, 100, 1,000, 10,000. So this is how you see a logarithm scales in real life. This one is clearly made by hand, you know, that is what people do in the old time. They did, and they put the points here and they draw the line. Okay, Kleiber did it with, well, I don't know if he did with his own hand, but this is someone doing it manually. Today you can do it with the computer. Lucky you. Yeah, you know, when I was a student, notebook didn't exist. We had computers, but not notebooks. So, or maybe when I was finishing, there were some that are not so expensive. I mean, rich people could have it, and they went to the laboratory with the computer, and they were doing. But my reports were made like this, handwritten. We had to do this plot. And in fact, we get from the store, we get this paper, millimetric paper, and we have log paper and semi-log paper to do this manually. You know, we had it. Well, just all time. Any question?
I have one, but it's a weird question. Why there is a woman is right in there, not man, just woman? Because all the other one they're like dog, rabbit, but not human.
Well, I can see here dog, goat, woman. I don't know why it's in particular market. You have to ask this guy why with care, but we can see the data includes men and women. I know that. I mean, in some animals, there is difference of size between male and female. So, if the gender is relevant, if the sex is relevant to classify the metabolism. I mean, for example, you know that in spiders, the sex affects a lot the size, or bees or something like that. So if you say bee, it is not very clear what you are speaking, if it's male or female. And in human, I don't know if it's so relevant, but it's a valid question.
Okay, thank you.
At the end, there is nothing in particular about any animal here. What you have a label that this is okay. This is a whale. This is an elephant. That helps you to kind of imagine them. But what we really get here is that you have one animal. We don't care the name. We don't care the sex, and we have the weight, and we have the metabolic rate.
Okay, I get it. Okay.
So. Valid question. I mean, poor questions. Okay, let's talk again about the robots are coming and see how fast they are coming. Moore's law. I saw a documentary one of these days about this processor. Okay, I can tell you too many stories about that, and this is not even the you see. This is not very updated, but you get the idea how the numbers are growing, no? And I got the data. I think I got it from Wikipedia, processed it, and I found that they essentially you see you should be able to recognize that this is what they call exponential growth. Okay, this is the shape. It's like a what they call. Some people call like a J or like a hockey, you know, people who play hockey, the hockey bar, I don't know what is the name. But it has this shape, that's an exponential growth. That is, you should be able to recognize this. The same way that you recognize this is a line, you should be able to recognize that this look like exponential growth. So yeah. If it's exponential growth, we will expect to have logarithm in the vertical, but not in the horizontal. In Clever, was a power law, we have log. In the exponential, we have semi-log. Okay, so the log is in the count, but not in the date. Date here, by the way, is year, and the initial year is 1970 or 1971. Okay, and these are the numbers. Clear here? We have log and we get a line, so we can do the log. I'm explaining again the same idea. Log y versus x, and the original formula is this, and you get. So the coefficients are going to be the log of the initial value plus the log of the growth rate. Okay. And voila. You take the same plot, you replace, and you get the coefficient. Very, very, very easy. And you get this number. Now, this number are not very useful, to be honest, because you get a log of count depending on there is not an easy interpretation of this number. But we can, well, they're just showing that they match well. They are a good thing, okay? But if you take the exponent of the coefficient, This is new. We take the exponent of the coefficient. Well, we did before, no? Now we have two numbers, the intercept here that multiply this number. And this is the interesting number. Every year, the processing power grows by a factor of 1.4, 40%, 41%. Okay, this is the result. This is Moore's law. Every year, the computer capacity. Well, this is a little more complicated. This is literally the number of transistors, but it's a good approximation of the computer power. It's kind of how much thing you can do in parallel, or how much memory you can make, how much storage you can have. Well, there may be more things to the formula, but basically the first idea is at the first approximation, this is a computer power. But what's clear from this approximation, you see the line fits very well to the data, and the line slope, when you take the exponent, and this is the important part, that you take the exponent, you get 1.4. So what's 1.4 here? Is 40%. Question: how many years to get twice the power? Okay, I will let you think about that. But if you got 40% in 1 year, and then the second year you have 40% of 40%, I mean, 40% extra, okay, let's make a quick calculation. You see my R?
Yes.
Okay, so in the year 0, we have 1. After 1 year, we multiply by 1.4. We went 1.45. In the second year, we multiply again by the same number. Oh, we crossed it 2. So essentially, how exactly, I mean, before trying, how can you solve it kind of mathematically? What we are saying here is that 145 to the power of 2 is a little more than 2. So this will be 1.99 or something like that, no? To get exactly you can go approximating, but instead of testing, we can solve the real question. The real question is, what is the logarithm of 200%, in the base 1.415? That is the question. Which power we have to raise 1.415 to get 2? And this is the result. So essentially, what we are saying is that in 2 years, you get twice the power. I mean, if you can do something today, in 2 years, you can do twice. In 4 years, you can do 4 times. In 6 years, you can do 8 times. In 8 years, you can do 16 times. No. Yeah. You multiply by 2 every time. In other words, how many years you get to have 10 times the power that you have today? 6 years, 6.6 years. Or think the other way. If you pay 100 today, in 1 year, you should pay half to do the same. If you're always doing the same, and you pay $100, let's say, in 2 years, you should pay $50. In 4 years, you should be paying $25. For example, for sequencing DNA, you expect that the price should be going down and down. So in general, the point is that computers are either getting cheaper, which is true at some level, or they are not cheaper, but they do more for the same price. So you probably know the experience that your cell phone today is doing much more things than the cell phone 5 years ago or something like that. No? Anyway, let's go back to the class. This data, by the way, I took it a couple of years ago. We can try to update it. Okay, that is the how we can see graphically how this thing grow. Just a comment I want to say, because this is a typical problem when people have to show the result. This coefficient that we calculated here, 1.45, it is the number that we have to multiply every time. But it's not the way that we say it. We normally say that we multiply by 100, so you get 145, and then you say how much is the increase. So this number, 1.41, we say is 41.5% of increase every year. When you say, for example, I don't know, the production of vaccine, let's say that we are producing vaccine for COVID and we increase the production by 20%. What do you mean that you increase by 20%? You mean that you multiply the number by 1.2. If you increase by 50%, you multiply by 1.5. If you increase by 100%, you multiply by 2. Okay? I'm just trying to clarify what we say when we say we are increasing by 40%. And the key word here is increase by. So you have something, you have, I don't know, there are money in the bank. And if you have, let's say, 1,000 liras in the bank, and if you say, my investment increased by 20% last year, what do you mean that increased by 20%? Essentially, you mean that the number that you had 1 year ago, you multiply by 1.2. Okay, I have like a question mark in your face, but this is super relevant because I have seen people that read the paper and they don't understand what is the paper, because when we are seeing how the production of some metabolite increase or the concentration of things increase on the number of cell increase, and people get confused when they say the number of cell increases by 100%. What do you mean? And the point that you have to keep in mind is this: increasing by 100% is very different than decreasing by 100%. Increasing by 100%, it means that you get twice. Decreasing by 100%, it means that you get 0. It's not symmetrical. I see too many question faces. So are you okay with this explanation or not? Do you want to think about it and try it later? Okay, let's do something practical. We have a little time before going for lunch break. Let's do something practical, okay?
Okay.
Why this thing is one here? Exercise. I want you to go to this website. I will even click here. I have some data, not the correct button. Okay. Error. In fact, this is not the one, the good one. Let me go to the. I will give you the correct link in a second, okay? But basic point is this. NCBI, as you may know, is one of the big databases of genomic data. There is also a European one. They have essentially the same data. There are three databases, a Japanese, an American, and a European one. I know the American because I worked with them, but the European have the same information. They synchronize each other. But for today's class, I'm going to see this is the called the short read archive. It contains all DNA reads made with new generation sequencers. And we want to see how this data is growing. Okay. So this is the web site. And if you can take a look. But let me go one step further. What I want to show you here is this. I have a database here, but let's use the real one. In this class, I have data that I got a couple of years ago. But let's go to this address. This is the one that I want to open in new tab. This is the plot we want to do. Okay, let's close plan. Okay. I give you the link, you should get the same page. And if you see, they have a plot here that is 2009 to 2020 to right now, beginning of 2021. Okay, my data is kind of up till here. Then you have the vertical. What is the vertical? Size in terabases. And you should see that you start with 0, 10. Well, this is probably 1, to be honest. 10, 100, 1000. So the vertical scale is logarithmic. Okay?
Yep.
And here's the data. So my suggestion is that you get this data. I will open in, probably you can copy, save link. I will open it in a page to show you, but you can do directly save link. Still didn't got it. Okay, anyway, we're going to see it. Let me see if I can show it to you here. Just a quick look. Okay, this is, you have a line that says date. They are comma separated, and the date is in quotation marks. So you have, this is the data we're going to load in a minute. Okay. So going back to the example is this. The plot, we should be able to do a plot like this. Okay. How you do it? And then we want to do the plot. Okay. Let's do the plot and then let's do a model. Okay. In this case, the grow started faster, but then stopped. The growth rate is not the same. The growth rate at the beginning is very fast, but after I don't know 2013, the growth rate is not so large. So we may have maybe the linear model will not be fitting all that. But let's see what we can do. Okay. You still have an average growth. Okay. Let's do it. Okay, you write your comments in the chat, your proposal of thing. What is the first step? What is the first thing to do? The sooner you answer, the sooner we go for lunch.
Did we import data?
Second?
Import the data.
Exactly. That is the first step. Very good. In fact, I will say that the very first step is to make a project for this class, a new project, new directory, new project. And I'm going to call it what we say, the 2021 01 04 class 24. That will be my name. Okay. To have an environment to put everything. Pum, 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 pum. Then okay, let me turn off my camera because kind of the computer is struggling too much with the camera on there. Okay, then we have to move the data. I have to move the data that I downloaded from the download to this folder. So let's do this. Let me open a show folder in new window. And I have my download here. And I'm copying the data. Short read archive statistics. Okay, I got it here. You see? I went to my downloads and I move it to the correct place. Okay. One alternative is when you go to the NCBI, you have the download and you have the option of save link as. And when you got the save link, you can choose where to store it. Okay, here you can choose somehow what is the folder that we are using. Okay. The point is that life is much easier if you put the data in the same folder. I mean, you make a project folder and then you make a project, you have a project folder and you put everything in that project folder. Okay. Okay, then we will make a document to store everything and we'll say R Markdown and I will say I'll learn to create empty document. That is the easy way. So we don't get any dirty thing. So here we say title, practice class 24 and author me. You put your name, date, January 4, 20. I am forcing myself to write 2021 because, you know, I am still writing the old date, the old year. When we use checks, it's always the problem that you write the wrong check. It's super typical. Okay, so how we read the data? I'm going to save this like
with read CSV.
Perfect. Just an idea. Okay, so I will do something like that. I will, and we have to give a name. We will call SRA because I want to have short name and assigned. First thing first. Library reader. The new way to read. No? Second, SRA will be the rest of real CSV. And CSV applied to which? To SRA data, SRA statistic. I press tab to get this listing and voila, get some blah, blah, blah. Okay. Okay, this will be fine for now. We can do something nicer later, but for now it is fine. Let's take a look of the data and it looks fine. But let's write here the comment. What we did first, real data. insert R block, and from the history, I'm going to copy the thing that I did. This one, this one. The view never in the RMD. Okay, this is one of the errors that I got a listing of all the errors that I found in the exam. And one of the common errors that, well, not common, but some people did this ugly thing. There are two commands that you never put in, well, at least two commands that you never put in a Markdown file. You never put view, and you never put in import. No, I don't know what is the name. Install packages. Yeah, these two commands should never be in an RMD. You get less point if you do that. Because they are things that depends on your machine. It's the way that you handle your computer, or how you see in your computer. They are not part of a document made in paper. Okay, remember that the goal of this course is to write a paper. So view is not part of the thing that you put in the paper. Install packages is not something that you install in the paper. Okay, we have a SRA here, save. Now what do we do? We want to get the, well, you got, let's see what is SRA here. Let's test. Worker, yeah, and here we got the rest. You see that, by the way, there is a trick here that we get underlined every three numbers. So we know that these are thousands, and these are millions, and these are billions. So you have bases, open access bases, and byte. Okay, for us, probably bases is the important. The difference between bases and open access bases is the following. In many projects, you get the money for doing your research, and you have to publish your data, but you want to store your data secret for a while. So there's some data that is in the database, but it's not open access, it's not public yet. That time that between you put the data in the database and everybody can access it is called the embargo time. An embargo are like 1 year, 6 months, maybe 2 years. So the difference between the second and third column is how many data is embargoed. Okay, what we want to plot here? Maybe we should see this again.
Open access bases to open access bytes, I guess.
But look at the plot. The plot has 2 lines. But let's say the blue line, for example, that is easy to see. It says total bases. Okay? And the horizontal has the year. Okay? And the vertical has the total bases. So what we plot here?
Date versus open access bases.
Or just bases. No, we don't need to open access bases, just bases, because total bases is bases, okay? Data equal array. And will it work? Will it work? Error. Okay, I will tell you what happened here. What happened is that the plot work with numbers, but not with character. Date here is character. So there are two options. Well, there are many options, but the two options that I have in my mind. The easy one is that we add a column with the serial number. But probably the most correct is this one. Let's go again to load the data from the with the tool here. And there is one detail that will help us here. So I'm clicking import dataset. You know this thing, no? It's a tool that will help us, and we are essentially going to do the real CSV. But there is one little change that we want to do here. So this is the looking, it's separated by comma. So really this is B, it looks fine. Yavash. Okay, let me turn off the camera, make it faster. Okay, I will be careful that the name is correct. Some people put funny names here in the exam, unnecessarily. This looks fine. I will trim this, but there is only one point here, that the date is here as a character. And we want the date to be a date. Okay? How we do this? We have the option here to choose it like a date. Now, here is a funny character, but let me explain to you. Let me cancel a second. What we have here is the date as a text in the American format. So the first value is the month, then the day, and then the year. You can realize that, for example, for 17, it means April 17 of 2008. And the first is not very clear, but this is clear that 18, 19 cannot be month. So these are day. So we have to have month, day, and year. Well, and in R, they use a format that, to be honest, is used in many systems. It's not very human readable, but with sometimes you will learn it. So percentage M will represent month, percentage D will represent day, percentage Y, big Y, represent the year with 4 digits. So it's exactly what we have, month, day, year. So we just say OK to the default. And now you will see that the date is understood as a date, and it says year, month, day in a way that is much useful for us. So we import, and you see that the command changes a little bit. Let me go to the source, and we are going to update this line here. History. This is the command that we really want to use. I will put it in the second column. You remember we showed this when we were working with factors. So this one extra parameter is not taking, this is the old I'm going to comment, but just to compare. Here we are saying read everything by default. Here we are giving one more instruction. Read everything, but let me tell you that the column date is a date, and the format of the date is month, day, year. And now if you see, if we do the plot again, and now it works. And there is a gap here, you see, because the first day and the others are. There are many points, and this is based on time. So I think this is a good idea to use type equal line. Okay, so what we are going to do here is this. Now we can plot, and we're going to plot it here. R. And just, I mean, both are valid, but if you see the lines are easier to read and faster at the same time. Okay, so we are going to go to the lunch break, but I will give you with 2 questions here. let's notice. Let's see what happened. First, we have to do it in a logarithmic base, and second, we have to find the average growth rate. Okay, there is a comment here that we want to omit, so we're going to go here and say show warnings. No, apply. I don't know if it's a warning or message, let's say. No, it's message, so I'm wrong. So nothing about warning, but message false. And real data, and the rest will look like this. In a bigger screen will look nicer. We will see in a minute. Or we can do other plot, whatever. And this is the plot that we did, okay? Bases, but the bases here are not in logarithmic. So your work is plot again in logarithmic scale. Then evaluate a linear model for the logarithmic scale, meaning, to be more clear, semi-log, with essentially with log in the vertical, not in the horizontal. Okay, these are the questions that